Hello, Riley.
Hello.
Thanks for presenting today.
Yeah, no problem.
Hello,
Hello.
how are you?
Hello.
How are you? You good? Cool. The name here, Relinga. Sorry if I don't pronounce the name correct.
No problem. I mean, you pronounced it pretty well.
All right. Okay. All right. Jakob, how are you?
I am happy.
Next chapter, you're gonna give us the transformer anatomy, right?
Sure.
Oh, nice. I'm really excited about the transformer anatomy because one needs to have understanding on how the transformer really works, right?
Well, I think I'm more excited now about text classification because that's what you most of the time do.
Exactly.
And if you don't understand how the transformers work under the hood, you still can use them. So I think now our meeting today is very practical about how to actually do things.
Exactly. So especially for me, that's what I do. Text classification. Yeah, that's yeah.
How much time should we wait?
I think it's already time, right? A minute past hour. We can just get started, I guess, since it is an hour. Right.
Yeah, sorry. I think
you can share your screen, right?
yes. I forgot to enable that on Zoom on this computer.
It shows on the bottom line as share screen, green button.
Okay, I have to. I just have to go through system preferences, but I have to. It's telling me.
Yeah, it's a Mac. It's a Mac system, right?
Yes.
Yeah, I know. The first time when you join, you need to do that. In fact, it will ask you need to restart your computer for it to. You'll be able to share the screen for the first time because of the security issues, I guess.
Now you may want to unmute yourself so that we can hear.
Am I unmuted?
Yes, we can hear you perfectly.
Okay. So I guess, should I start?
Yes, you can.
Okay. So this chapter is on text classification. So it's not really focused mainly on the focus is not on like the transformer architecture. I think that's next week. It's more so on the application of transformers. And this is kind of like a very common application for text classification. For transformers is text classification. The goal in this section of the data set that they're using is a Twitter data set for emotion recognition. So basically, you get a Twitter message and you have to classify whether the emotion displayed in the Twitter message is one of 6 categories, which is, I think, is love. Not sure what the categories were. It was love, surprise. I think I can look at the error analysis and see exactly.
Here you go. Yes.
Yeah, it was sadness, joy, love, anger, fear, surprise were the 6 categories that were labeled in the data set. So this first part is mainly loading the data set, and then displaying, kind of doing some analysis on the data set. So figuring out how many, what the test train split was. So the testing data set was 2,000 examples, while the training data set was 16,000. So not, as far as data sets go, not like the largest data set, but it's still a pretty decent size. Yeah. And then displaying kind of, I guess, examples. So one example tweet was, I didn't feel humiliated. And then the column names are pretty straightforward. It's mainly the text and the labeling, which is the emotion. And these labels do have indices from 0 to 6 as well. Yeah, so it's displaying 5 examples. Since it's Twitter, there's a maximum character limit. So in a lot of these cases, the length of the text is pretty uniform. So this sidebar that they're going over is, what if the data set, so the data set they're using is on Hugging Face Hub. So they could just use the Hugging Face API here to just load the data set. So it's pretty simple that they don't need to, like, it comes in a format that is very compatible with Hugging Face, because it is coming from Hugging Face Hub. If your data set is not on Hub, then it usually, in this case, it's getting a file from Dropbox, downloading that file, and then loading the data set with as a CSV file, or yeah, it's a text file, and then it's loading it with in CSV format, with the separator being a semicolon. So that's mainly what it's doing there. Not sure if we can look at this file. I have it on my system as well when I was running it. Yeah, so these are the examples. I think I can do that now. So yeah, this is like the text file. It's separated. So it's actually the same data set. But in this case, it's like assuming, like, if you had another data set that you want to load, how you would do it in with the Hugging Face load data set function. So you see the text, and then there's a semicolon and the labeling of this text. and everything separated by new line.
Maybe can I point out something when we look at the data set over here, something which not related to the techniques, but to the data itself. We see that they have, every line has one column, one label, which is one of the 6 labels. And they don't have a neutral value. Sort of, if somebody says, I just got up in the morning, the model will be trained to give some interpretation that is sad or that's angry because it doesn't have a neutral label. So this is I think, a fault with the data set. It could be that they only have emotional twitters, tweets, but when you apply this to sort of non-emotional tweets, you will get sort of very strange. The model will guess what it could be, and this usually is sort of bad for using this kind. So you get bad results. Now this is not, so it's not a problem with the presentation. It's just, I think we should pay attention, or we should be alert that if you have a classifier without a neutral column, then when you have a neutral text, you will get, the model will guess, and you will be surprised about what it guesses because it's just a guess.
Yeah, exactly. So yeah, there's several examples. Like, I didn't feel humiliated. I wouldn't call that sadness. I would say it's more like a neutral kind of tweet. Or another example would be, I didn't really feel that embarrassed. So yeah, it's more so like a neutral tweet, because they're saying what emotion they didn't have.
Yes. So I mean, as you said, like some tweets are not actually expressing what it shows here. It really depends on the annotators, because these people are not perfect and they were given just guidelines. And sometimes they don't actually follow the guidelines, or they mistaken what the guidelines is. And yeah, I think that emanate from maybe simply from the annotators.
Mhm.
And also, yeah, I mean, the good point by Yakov about the classes that there isn't any neutral. That's a good point. I think they should have a neutral. For example, we can have this data. Yeah, I mean, it's really reasonable point to have neutral, so that we don't actually classify something that is neutral to any of these classes. Yeah, thank you.
Mhm.
Yeah,
Now,
I can't even imagine a real application of this classifier outside of academia, because anywhere you're going to try to classify to emotions, how are you going to guarantee they all have an emotion? You would almost have to pre-process your data in real world by eliminating all neutrals first. So you might as well include it in here. So you could see that nobody really used this for a real situation. Probably, it probably comes out of academia. But anyway.
Yeah. Yeah, so basically the sidebar is just talking about loading like a custom data set via a text file. So the main point in this section is, so you can kind of set the format of your data set if it's loaded through the Hugging Face hub. So for example, like, you can set the format to be pandas. In this case, if you do set the format to be pandas, then the data set will be converted to a data frame. And you see an example of the data frame in Jupyter Notebook. It's basically the same thing we saw earlier. And then you can, sorry, there's a train in my background. But you can also make integer labels for the emotions. So for example, like, sadness will be labeled 0, anger would be labeled 3, love would be labeled 2. And this is mainly useful for computation purposes. And then you can also look at this. So they're doing some analysis, and then they're going to also dig more deeply into the data, just to explore the data sets more and make sure that you're able to classify the data without without looking at like tricks in the data that are kind of super surface level. So one example is like class distribution. Like if your classes are heavily skewed, you could actually have good accuracy on the model, but it could be because you're always predicting like the high frequency classes. So you want to make sure to look at the class distribution beforehand so that you're not like you're not using these tricks, or your transformer is not using these tricks to get good accuracy. Or it's not using information that is surface level. So for example, in this case, the data is pretty skewed. Like most of the tweets have labeled joy, and not a lot of tweets are labeled surprise. Like you see, there's like 5 times as many tweets, more than 5 times as many tweets that are labeled joy than labeled surprise. So there is class imbalance, and there's certain ways of overcoming this class imbalance. One would be oversampling the surprise class. So one example could be like you duplicating the surprise tweets, or tweets that were labeled surprise, just so that you get like you see as many surprise examples, or like your model sees as many surprise examples as joy examples. Another thing would be you can undersample the majority class. So undersample joy. So you take maybe like 1 in every 5 joy tweets so that it lines up well with the number of surprise tweets that you have. This is, I don't think undersampling is used so much in practice, mainly because especially like researchers will value like the accuracy of the model by and they want as much data as possible. So intentionally undersampling is not something that I personally see often. And it's certainly not something that makes like a researcher going for high accuracy happy. And then the other example would be, or the other way of handling imbalanced data sets is just gathering more labeled data from the underrepresented class. This one is like not something that is easy. I mean, labeled data is a lot of cases hard to come by. For like I mean, like just gathering more labeled data, it's time consuming.
I have a quick question just to confirm. So it's pretty much having to balance an imbalanced set in one way or another just as important in deep neural networks and in transformers as it was, pre-deep learning, when you'd use, support vector machines and gradient boost and all that stuff. Does anyone know? Is it pretty much the same game?
I would say it's pretty much the same game.
So you do it, definitely. It's really important then. Okay. What else were you going to say there?
Yeah, I would say like it is pretty much the same game. Like neural networks, depending on the architecture, some of them are very in case they like to find shortcuts. So like class imbalance would be like a shortcut that would be that is something that like a neural network would pick up. But I think it's the same as a lot of like classical machine learning architectures, like you mentioned.
Okay. Cool. That helps. Thank you. I would mention, of course. I'm sorry. Go ahead.
I just wanted
there is one other reference I would point to is at least as far as it relates to images. I've heard Jamie Howard of FastAI say that a ratio of about 3:1 is not anything to worry about, but when it gets beyond that is when you would begin to apply some of the techniques discussed. And up to 3:1 ratio, he doesn't think that any kind of technique is that imperative to apply.
Thank you. That's very helpful, because that means you don't have to get them exactly balanced, right? Either.
Yeah.
I just wanted to point out that with unbalanced data, you have two problems which are distinct. One problem is that if you give sort of one majority of the class to the model, it may learn something imbalanced. Sort of the model may pick up the imbalance in the data, and there you have to decide maybe that's what you want, maybe not. But the other problem is that when you compute the precision on the results of the model, if you have a very high imbalanced classes, then you fool yourself. Sort of you think that if you get a very high precision, that your model is very good, but you just gave it a very easy task. So when you think about balancing of the model, you should think about this as two separate problems about what it does to the model and what does it make to your own understanding of the results. And now why I'm saying this is because if you have many classes, there are sometimes situations where you cannot oversample everything, sort of, or where it should, some of the classes are naturally low and they should be low because you want the model to assume that it's very rare. But so you should then know that when you see a high accuracy, that this is not a real story. So the baseline is already 90%, and you have to get much better than that in order to show any real uplift.
Mm-hmm. Yeah.
I also want to add, you just mentioned that gathering more level data is really expensive and time consuming. But one way that one can automatically use distance supervision, there is a paper that share for that you can distance supervise way to automatically annotate some data and just augment it with the existing data set. And some works shows that it's really better or than oversampling and stuff. Yeah, so this one is related to this. There are many works related to this where you can just use a model to annotate some data and augment them with your existing data sets. Yeah, thank you.
Mm-hmm.
So in what circumstances would you want to keep the data imbalanced and then maybe run it with a super simple classifier or something, or even untrained to get a baseline? Let's say that's 85%, and then try to improve it. What is the use case where you actually want to keep the imbalance for some reason? I mean, Yakov, you kind of intimated that sometimes you do that.
Cases where you want to keep the imbalance.
Yeah,
I think Yakov, I never heard of that, but I think that's sort of being
yes,
said.
Yeah, that's a good question. Yeah.
Now, what I would say that if you really have the thing is, the classifier takes, say, into account the, say, if you have a class which is very, very rare in 1 second. Now, okay, maybe I take my argument back. Maybe I take my argument back. Maybe you shouldn't.
Yeah, so you do have a point. I've heard, and in fact, I was trying to look it up, but I don't have the reference easily at hand, but I will post it later on Slack. One of the NYU profs actually brought this up, which is to say that if the data in real life is in fact imbalanced, let's say you're classifying a set of observables in a cell, and you know, in a biological cell, and you know that certain entities are less in nature, but you improve your training. He had a comment and a suggestion as to you still have to do something so that the trained classifier doesn't believe that in nature, that when it applies, that it's equal. So your point about, thinking about getting the model better, but at the same time, having the model reflect what actually exists in nature, if you're trying to do that, is an important distinction. And he had a suggestion as to how to, in the final step or something, you still, after having somewhat balanced the data set, you still want the classifier to realize or to do a good job in nature or when facing the actual distribution of data where the data will have imbalance. And now I don't have the exact stuff in front of me, but I'll see and post that link of where he talks about it and what he suggests that you do. So it's not true that in all cases you would want to, you may want to fix the imbalance, but you want the classifier to still stay true to the imbalance that it finds, that it will invariably find in the data.
Yep.
Mm-hmm.
Just a quick question. Has anybody used a BERT-based model or any sort of modern neural network or transformer model to automatically classify like thousands of topics, like 3,000, 4,000? People do that with transformer models? I know there's extreme class. There's a world of extreme classification that sort of came about before all this a little bit, and I've seen stuff on that. A lot of that comes out of product classification, where you may even have tens of thousands or hundreds of thousands of products. But I'm talking about more like topics, because I work with topical taxonomies that have 5,000 hierarchically ordered topics. Is it crazy talk to try to do that with a BERT-based model, or does it seem reasonable?
I think it seems reasonable. Yeah, I haven't done it myself. Like, I haven't used BERT like at like a production scale level. So,
yeah, I mean, almost everything you see is like 2 classes, 5 classes, 10 classes.
Yes.
You know what I mean? So, and I've never met anybody who's actually done serious auto classification using a transformer outside of pretty small sets, under 100 of classes. So.
Yeah. Mm-hmm.
Okay.
That is just a comment.
Like your question.
While
I like
what you said is true, it doesn't in the NLP domain, it doesn't apply in the images domain, because in the images domain, for example, these days, transformer-based models are competing to be among the best classifiers, and there they classify 1,000 classes or even 22,000 classes on ImageNet.
Got it. Yeah, that adds a little bit of confidence that it will work with NLP as well with the attention.
Yeah.
With transformers.
Are you doing this right now on your data set? Well, I like your question very much. I don't have experience with that, but I was working on NLP classifications for products, and I was asking the same question myself. So if you get some experience on that, can you share it on the Slack?
Yes. Also, I don't know if you are aware of the extreme classification literature, and there are some libraries and things. So you may want to, if you have to readdress, I'll share whatever. But I haven't done any of the extreme classification stuff. But it's literally an area of that. If you're going to do product classification at scale, you should look into. Although, again, I'm having a little hard time reconciling the extreme classification techniques with the somewhat more modern,
Yeah,
the most recent with transformers, let's say. But that to me, that's just been reading stuff. I haven't done anything with that, Yakov. Although I have set up some sort of automatic classification for my topical taxonomy, but not using transformers. So, but yes, I'll share if there's anything, or you feel free to ask me more questions if you want.
Yeah. Yeah, like I haven't explored the larger kind of NLP data sets. The ones that I've mostly seen are kind of like the MNIST data sets for NLP, kind of like MNIST has like 10 classes. This has 6 classes, kind of like the kind of teaching example. So I haven't seen like the kind of the classes more akin to, I guess, ImageNet for NLP. I just haven't explored.
Yeah, what's nice on my end, I haven't been able to do this because I have to sort of be driven by what I need to do at work. But the nice thing is, for 7 years, we've had our content manually classified by a company every day. They classify, so I have a pretty substantial training set. But oh my God, the imbalance is insane, right? There's some really narrow topics, and there's topics that have nothing even, and so forth. So, but anyway. Sorry, guys, I don't want to derail us too much. Thanks.
Yeah, so another thing that you don't want your transformer to look at is kind of just the length of your text. If it's using like the length, how many kind of stub characters are at the end of your text, that would be kind of something that you don't want your model to look at. So what I mean by stub characters is like basically when they feed this data into the model, they're going to do a token. They're going to encode them into tokens, or not encode them, but they're going to do kind of transform each subword into a token, and then truncate the length of each tree, and then make sure that they have kind of a standard length. Just for computation, for doing like tensor.
So I have a question. I'm sorry. Are you saying that it's important to not just to be under the maximum size for the model, but also to even out the length of all your text within that size?
For the training set, for the training set, yes, because it does help computationally, and we'll see that later during like batch computation. You want to make sure that your text is kind of the same size. So in a lot of the cases, if it's too long, they'll truncate it, but if it's too short, then they'll add these white space characters.
The padding.
Yeah. Yes, they'll pad the text so that it's kind of uniform length. In this case, we don't want cases where the network is looking at the padding as like as an indicator of which emotion that tweet is. So one way of kind of making sure that the padding is, or kind of checking that the padding is not going to be an issue, is if you look at the length of the tweets and make sure that there's kind of an even distribution of, or that the distribution of lengths of the tweets is the same distribution for each emotion. So that's what you're seeing here, is that it's hard to see the labels, but you see anger, fear, joy, love, sadness, surprise, and they're all sitting around a mean of like probably 18 words per tweet. So I would say these distributions are pretty similar. There's not one distribution that is like when the mean is hugely different from the other distributions. So this wouldn't be an issue in this case, but in other, you can imagine cases where the distribution of lengths of one of the emotions is a lot higher or lower. And in that case, it might be an issue where your model may look at like the padding and be like, oh, this might be representative of this tweet because it's shorter on average.
Yeah, so sorry for taking us back about the oversampling. So I was thinking like, so if, for example, if I have a sentence in one data set, it's called I love this cat, and we do oversampling. So when we do oversampling, we maybe locally we take that sentence, I love this cat, and now we create more sentence. So do you think, I'm thinking like, when we already have a sentence and we duplicate the same sentence, will the model learn something different? Because we oversample from the same set of whole, I don't know what the oversampling means. Do we mean replicate the same tweet or the same text? What does that mean, oversampling? Do you understand the question? So
yeah, so you're talking about oversampling here.
Yeah.
Yeah, so a lot of cases, that is the easiest thing to do is to when you're oversampling is to duplicate the same tweet. So you're seeing the same in one epoch of training. Let's say you're seeing the same tweet multiple times for surprise. They don't do any. They talk about imbalanced data sets here, but they don't do anything in this notebook. But that's one example of oversampling. Another example of oversampling would be, I can't think of an NLP equivalent, but in computer vision, they do an oversampling, but they're kind of transform the data a bit. So things like
augmentation.
Yeah. So like one example would be like they would kind of tilt the image a bit, or they'll flip it.
So the interesting thing, though, in your question there was that, yes, just duplicating helps, because even though you're not giving any more information theoretically to the algorithm, you're tricking it into not using its trick. It's kind of like you're hiding something it could erroneously use to predict the class, right? You're breaking. You know what I mean? So even though, maybe someone can explain it better, but even though it's just duplication, you're not adding any more information. You're making the model so it can't use a particular pattern that would not a pattern you want it to use.
I recall having read that if you have the same sentence appear a few times, then this may help the model to overfit, which may be not a good thing. So that the model thinks that if you have exactly that sentence, then it's that category, but if it's slightly different, it's not the same thing. So I think that all the techniques which you do in data science, you always come with a trade-off. If you do too much of it, you have a price to pay. So I think there is a downside of oversampling, which could be overfitting, which means that you have less generalization. And of course, that's something which you would have to try out and to see how so it's very experimental. It's not something they can have a fixed rule how much impact you have.
Mm-hmm. Yes. So yeah, it also depends on how much you're oversampling. So like I think a 5x factor of oversampling wouldn't be too bad, as opposed to like if you're oversampling the same tweet hundreds of times.
Mm-hmm. Now, one thing which you do never want to do is you never want to oversample in a way that you get the same data point in your train set and into the test set or into the validation set. You want to make sure that the data sets are completely separate from each other. So if you would, for instance, oversample and then split, then you could have that the train set and the test set maybe contains the same data points, and this would completely mess up your awareness about overfitting. That's a sort of different point.
Yeah,
so,
I think that's leakage, right? It's the famous Kaggle stuff. There's always leakage, and then in real world, you screwed yourself and cheating because you're cheating across the set.
So one recent paper
Good point,
I read,
thank
I
you.
just share the link. Basically, what they do, for example, I think it may also be nice, maybe like if one wants to oversample, is so generally Twitter does not actually allow one to share tweets. So what they do is like they basically, I think, is it paraphrase the tweets, and so it really means the same thing. So I was thinking like now if we have a data set we want to oversample, maybe we can replace some with synonyms in the data set. Like if something say, I love this cat, maybe I can write something that shows you like the card, you know? So it means it's saying there's something, but yeah, so I think this is a cool idea to substitute some existing stuff from the data set, paraphrase it so that you oversample, you increase it instead of just replicating it.
If you look at, I think Srinivas, or there's imbalance learn. There's a library too that incorporates a bunch of the stuff from these papers. Imbalance learn. It was posted on our chat.
Mm-hmm.
And the thing about it also is, that's what you posted, right? And then the thing about it also is, there's also another technique which is translation. So you actually translate from, let's say it's English, you're doing your classification on, to another language and back. People do that literally. To upsample. Literally, just you translate it, and when you get it back in English, it's different, but it means the same thing.
Back translation.
Yeah, there you go.
Okay. Yeah. So yeah, those are a few ways of oversampling. And then as far as like length of the tweet, this is mainly saying that the distribution looks to be the same based off the box and whisker plot for each emotion. So we don't really have to worry about that with this data set.
Can I make a comment over here? When we talk about the length of a sentence, there are two concerns over here. One is about the data, sort of which we discussed right now, is that if you have a short sentence, maybe it's more anger, and if you're a long sentence, maybe it's more happiness, something like this.
Mm-hmm.
And this is data quality, so that's one area. And then you have the question about performance, which is that if you have, say, 200 very short sentences and one very long sentence, in order to put it into the GPU, you have to make out of it a rectangular tensor, which means you have to pad all the short sentences to get to the same length as the long sentence, and your GPU will basically waste a lot of time to crunch through the numbers of zeros which have no meaning itself. So by having the sentences in each batch to have a similar length, you use your GPU more efficiently. And there are different ways of doing that. And one good way is that if you sort the sentences by the length, so that at the beginning you have the short sentences and later on you get to the long sentence, and each batch is sort of a similar sized batch. So you have the first batches are processed very fast because they're very short, and then the later batches are taking longer time because they're actually longer. So you can deal with that. And this is a only a computation issue, that you are more efficient by having a is similar length within each batch.
Mm-hmm. Yeah. Okay. Yeah, that's a good point. Yeah, so the next section we'll be going over tokenization of the text. So this is how do we get the text data to be kind of numerical data, or be like a numerical feature tensor that we feed into a deep network. So one example would be character tokenization. So this is splitting up your data, your text by character, giving each character a label, and then transforming the label into a one-hot vector that you can feed into like a network. In practice, I mean, if we're to kind of use the one-hot vector as a with like a large vocabulary, there's a lot of like if there's a lot of like characters or a lot of we'll see this in the word tokenization, then having one-hot vectors is pretty large, and it's sparse kind of data structure. So I think the one-hot vector kind of scheme is mainly used when you don't have a ton of classes or labels that that you need to vectorize. In this case, it's not as bad because characters, there's not that many like characters, or in this case, ASCII characters. But when we see with word tokenization, you can't use like this one-hot vector kind of scheme. And libraries like PyTorch, when they're doing kind of token embedding, as we'll see later, you can just use the labels instead of one-hot vector, because they don't want to do like the matrix multiplication between your embeddings and the one-hot vector. They would rather just index and use these labels as indices into their token embeddings. But yeah, in this case, for character tokenization, they do transform into one-hot vector. In practice, character tokenization is difficult as well, because it makes your sentences pretty long, or your text is going to be a very like long tensor, as opposed to things like word tokenization. And it's harder for like not just neural networks, but any kind of machine learning algorithm to grasp the semantics of like a text, or like any kind of higher level information based off of just like single characters. Like it can work in some instances, but it's not like a very practical, I would say. Yeah. Like you want to set your network or your classifier in a position where it can learn high level kind of information, and I think character tokenization is not going to do that. And then there's word tokenization, so splitting up sentences or text by white spaces, and then you have like a vocabulary of words that have labels, and then you give each word a label, and then you feed that into your token embeddings. The words are you can also have like special words, things like usually they'll have like a special token for the start and end of sentence. I think we'll see that in the next section as well. They'll also have maybe tokens for unknown words that are not in your vocabulary. Yep. The problem with word tokenization is that like your vocabulary can be very long as opposed to like character tokenization. It's still better than character tokenization in my opinion, but yeah, you could have a very long vocabulary and you could have like repetition in your vocabulary. So things like tokenizing versus token should be kind of it's the same concepts, but then your vocabulary will include all of the kind of conjugations of each word in the English language is kind of overkill. And you don't want, like, let's say you see tokenizing, but you don't see token. You don't want cases where you see token in the word, and because your training data set didn't have it, then it gets assigned to unknown during inference. So that's what it's basically, that's the drawback of word tokenization. So kind of the solution would be subword tokenization, which is, I don't exactly know what the algorithm is for subword tokenization, but the idea is you're not tokenizing words, you're tokenizing subwords so that you can, the word and its like its suffix or a prefix would be kind of two separate tokens. So you don't have cases where like a different kind of conjugation of a word is being assigned to an unknown token, as what happened in word tokenization. And the vocabulary is also, I mean, it's not going to blow up like word tokenization, but you'll still have a very large vocabulary compared to character tokenization. So in this part, they use like the distilled BERT tokenizer. They load it from Hugging Face, and then they do an example where they tokenize the text, which is yeah, the text is tokenizing text is a core task of NLP. So you can see that the tokenization, so CLS is the start of the starting token. Then they split token into token and its ending, which is izing, so tokenizing. And then these are just words. Text is a core task of, and then they split NLP for some reason. What this tokenizer split for some reason into NL and then P as a separate token. And then punctuation is usually its own token, and then the ending sentence. So you can string that together to form the actual to get back the sentence before tokenizing. And we see in this case the vocab size is 30,522, which is way higher than if you were to kind of do character tokenization, but it's a lot, it would perform a lot better. The other thing with character tokenization is like the thing with deep neural networks is that as you get deeper into the network, you want it to learn kind of higher level information. Like you want to learn, you want to kind of aggregate that information from the last layer and from like higher level patterns. And in the case of character tokenization, you have to make your network more deep. I would say, like, I mean, intuitively, you would probably have to make your network more deep than if you use character tokenization than word tokenization or subword tokenization, because you need more layers to kind of learn that high level of patterns. If that makes sense.
Yeah.
So in a lot of cases, just like subword tokenization is like the standard. They didn't really go over attention mask, so I won't go too deeply into that. But yeah, the tokenizer outputs like the IDs of the text, but also the attention mask.
Maybe we can just make a very short comment over here about the attention mask in this case. It basically says it's not connected to the attention mechanism inside transformers. It is a very simple concept. Let's say if you have a short sentence, hello world, and you have other sentences which are longer, like tokenizing text is a core task of NLP. So you will have to pad the short sentence by space characters. And the attention mask is just put zeros on them, that the language, the model will just not look at these at all. So the attention mask in the context of tokenization is basically masking away the padding characters that the model doesn't see them at all. So if you look at the sentence, you see that at every token which is relevant, the attention mask will be 1, and after that, when you have the padding characters, the attention mask is always 0, which means don't look at it.
Mm-hmm. Okay. Yeah, I guess the attention mask could also be useful if you're doing like causal models, where like you have a sequence and you want to make sure that it's only using like information before what you're trying to predict. Let's say you're trying to predict the next item in the sequence and you only want to use information preceding that, then you could use like a mask in that case to kind of mask out anything that happens after.
That's what's normally done when that's another use case of a hard-coded attention mask, exactly. Yes. Yeah. But when so for instance, if you generate text one word at a time, then you use this attention mask sort of not to look into the future.
Yep. Yes. And then the next section is just tokenizing the whole data set. So it does it by batches. And it tokenizes kind of examples by doing padding and truncation. So making sure that the shorter sentences are padded to the length of the longer sentences, and the longer sentences are truncated so that they fall in they have uniform length. And you want to do this for GPU purposes and computation purposes, where you want to feed in a tensor into your network, and be able to do tensor computation on the data and the batch.
I have a question. So I can see there they said you need to use the same tokenizer with your model. So before we tokenize our sentence, we need to check how the models, what kind of tokenizer the model use. Is that correct?
Before you tokenize, you want to...
Okay, can you scroll up a bit? Yes, so, okay, yeah. No, down a bit. down. Yes. Okay, here. There is a warning here. Can you look at it?
The warning?
Can you move a little bit? Yes, here.
Yeah. Oh, I thought you meant like a Python warning. Yeah, so yeah, I'm not exactly sure. Like they didn't go over exactly how the tokenizers are trained or how they're created. Like for word tokenization and character tokenization, it's pretty straightforward how to split your sentences. But for subword tokenizers, it's a little more complicated.
Yeah, but with Hugging Face, you don't have to worry about any of that because you instantiate a tokenizer from the model, or you instantiate the tokenizer from the model name. You always do that.
Mm-hmm.
So like your model name is a variable, and then you get the model, and then you get the tokenizer. So you always want to use and instantiate your tokenizer from the model you're using, so you don't ever have to worry about.
Yes. Yeah.
Basically, the warning over here says always do what we just said, because if you don't do it, you really confuse the network. Maybe you can explain it in this way, that the tokenizer translates your sentence into numbers, and he learns sort of how to match words or subwords to numbers. And even if you have a word tokenizer, you could have the same set of words mapping to different numbers. And if you don't use the same tokenizer for training and for prediction, then you will really confuse the model. It will make no sense at all. And for that reason, A, you should always make sure that you use the same tokenizer, and B, Hugging Face make it very, very easy for you to do that by just say the tokenizer is always tied to the model. So when you want to improve a model, if you want to fine-tune the model, you take the tokenizer which comes together with the model in order not to make that mistake.
Mm-hmm.
So also, just to add to that, what Yakov said is that it's not only that you need to be using the right tokenizer. There are different algorithms for word piece, for doing subword tokenization, literally. So the model may have used subword tokenization, but there's many different forms and variation, or at least a few different of those subword tokenizations. That's why Hugging Face did that, right? Is because you have to use the exact same one that the people who built that model used.
It's more than the algorithm. It's even that if you take the same algorithm, but you train the tokenizer on the text which you have. So, for instance, if you have a text, so you have to take exactly the same algorithm and the same data in the tokenizer. It must be 100% the same, and that's the reason why they need to help you with it.
Yep, thank you. That makes perfect sense. Cool.
Mm-hmm.
Shall we go on?
Yeah. Yeah, so basically they're tokenizing the whole data set, making it uniform length, and converting into a tensor. And then they also have like special tokens, as mentioned before. So you see a visual example of what it's doing. It's the input can be different lengths. It's making sure that it's padded to be the same length. And this is like the input batch. And then the attention mask would be just ones and zeros for one if it's for the number of words in the text, and zero for the rest of the text. And then so one thing that this section or this chapter does is that it tokenizes the whole data set at once. In a lot of cases, as mentioned earlier, like you might want to batch sentences with similar length together. In a lot of cases, you want to tokenize batches instead of tokenizing the whole data set. But in this case, since the data set is not that large, and it's also the task is not like like a super difficult task as far as NLP, tokenizing the whole data set is fine. And you do want to look at the lengths of your sentences before you like tokenize the whole data set. But yeah, if you tokenize the whole data set, then everything in your data set would be uniform length, which I think they're doing here. I think they're tokenizing the whole data set at once.
One comment over here, both in terms of the batching and in terms of the imbalanced data, in practice, you want to care about them and you want to do the right thing. But for education purposes, this book wants, first of all, to show the basic principles without destructing when going with all the fine details.
Mm-hmm.
So on the point of batching, Hugging Face has very good support for this. And you're just adding 1 or 2 more lines to your code, and you get automatic treating of all the batching in the right way, because that's what you do all the time. So there's a course where they go more into deeper details about the options which you have. So basically, over here, I want to say this section doesn't dive into the technical details, but there are standard solutions for that.
Yep. So once the data is tokenized to be the same length, the next thing would be to train a text classifier. So in this case, so you have like your token encodings, which are like the labels from that we found earlier, or we found earlier is the token encodings. And then there's token embeddings, which is like it's something like that Distilbert would have to kind of I believe it is already included in Distilbert, yeah. And it's the concept of like text to vector kind of would be like a token embedding, where it's transforming your labels or your label into kind of a vector. And yes, it's like an embedding space. And a lot of cases your embedding space will, if you like projected it onto the space, then you could do like vector operations on your embeddings. So like and see like if you like projected it onto 2D space, you could kind of see like groups of words that kind of semantically kind of belong with each other, if that makes sense. So it's a better kind of representation of your tokens. This doesn't go too much into detail over like the model itself. It does like a bunch of a deep network to encode your token embeddings into a hidden state. So this hidden state is your encoding. And then
so the encoder stack, just this is a question, that's where your attention layers are, right?
Yes.
Diagram.
Mm-hmm.
Okay.
Yeah.
Yeah, so the token embeddings are your dimensionality reduced one-hot encoding. So they're no longer one-hot encoding, they're dimensionality reduced, and then they're non-contextual because they haven't gone through attention, and then the encoder stack is where the attention happens in the transformers, and you get contextual techniques, right? Okay, thank you.
Yeah, so one of these columns here is one token, and then one of these columns here is one token. But the columns in your hidden state, as shown here, they take information from multiple tokens.
They're contextualized.
Yes, yes. And then the classification head is something that you can just attach to like your encoder. And then the classification head is what is used to do predictions. So we see. So there's two methods that it goes over in this book. One is transformers as future extractors. So the whole idea is that your encoder is frozen. So there's no gradients, there's no backprop, no gradient descent or any optimizer for these parameters. So your encoding is fixed, and then your classification head is what is receiving the gradients and being optimized. So you're basically using the transformer as a black box for future extraction. And then it goes over, so it uses Distilbert as the feature extractor, feeds in the text through the feature extractor. The sidebar is for TensorFlow, which I won't go over too much. So yeah, this is what it's doing. It's doing torch.nograd, meaning that it's explicitly telling Torch to not do backpropagation on the feature extractor, on the encoder. And then it prints the output. So it feeds in a sentence. I think the sentence is, this is a test. And then you get this tensor output from the feature extractor. Then it just takes the last hidden state. So it takes the last encoder layer. It gets the size. So in this case, the size is of each column is 768, and there's 6 of those columns in the sequence. One is just the batch size, since we're only feeding in one sentence. And then it takes only the first hidden state of the encoder. So in this case, it only takes one of these columns or one of these hidden states, and it uses that as, for the classifier. And I believe the classifier is just, the classification head is logistic regression. So think of that as like a one layer fully connected network. Yeah, so it just extracts the hidden state, takes the first one, the first column, and then yeah. So here it's just saying the format of the data to Torch as a Torch tensor. Then it feeds it into the model, make sure that there's no gradients flowing through the model, and then it just takes the first column of the last of the encoder, puts it back. So this is happening on the GPU when we feed into the model. Then it takes the tensor, gives it back to the CPU, and then converts it to NumPy array. Yeah. Then when it's evaluating, it will only be training the logistic regression part of the model instead of the the whole model itself. I'm trying to find the section where it defines the classifier. Yes, I think this is just extracting the hidden state. Yeah, it's so once you have the hidden state, you can project it onto a 2D embedding and then visualize it. So in this case, it's projecting the embedding onto different classes, based off different classes, and trying to find like hotspots in the embedding. In this case, it's a lot of the intuition comes because the classes themselves have relationships to each other. So like probably like joy, love would be more akin to each other than sadness, anger, fear. So you should see that the hotspots in sadness, anger, fear are look more similar to each other than joy and love. And surprise should be kind of maybe a mix between fear and joy in a lot of cases. So you should see that as well. And that's mainly the intuition that's produced from this 2D embedding. You can't really, I don't know if you can get more information out of this besides that kind of intuition. Here's where they changed the classifier. So they use logistic regression as the classification head. I believe this is just kind of like a softmax, fully connected one layer network. And then it uses uses XTrain, which is the kind of embeddings we found earlier, and then the labels of the data set, which is just the numerical value of each like emotion, and then it fits the data, and I think the output would be, this output is the accuracy of the model. So it's saying that's a bit better than random. So it I think random in this case would be
1/6 every one, which means 16%, something like this. So 0.60 is actually much better than random.
Yeah, it says it's a bit better than random, but I think that's
much better than random.
Yeah, they used a dummy classifier before. Down, so a dummy classifier is somehow
0.36, 0.35.
Yes.
That's twice as good.
Yeah, so in this case, the best performing heuristic is to always choose the most frequent class, which yields 35%. So the dummy classifier is mainly choosing, its strategy is most frequent. So it's labeling everything as joy. Yeah, this seems a bit, more than a bit better than random. Yeah, and then it's plotting the confusion matrix. So it's mainly the things that it gets wrong a lot is surprise, which it confuses with joy and fear. And then which is understandable.
Yeah.
Which gets confused with joy. pretty often.
Yeah.
The thing is, anger gets confused with sadness, and sadness to some extent, fear gets confused with sadness to some extent.
Mm-hmm.
Yeah. Actually, I think sadness was the highest class. It was either sadness or joy.
Sadness, joy is the top one, and sadness is the second one. So
Okay.
those joy and sadness are both high presented, and the others are lower.
Okay.
Yeah.
Yeah, so that is the first scheme that it goes over. The other method or scheme that it goes over is fine-tuning the transformer. So instead of freezing the encoder, it actually trains the encoder with the classification head. And you see it here.
So yeah, so I was having a doubt in the previous section. Like if you don't use the gradients to convert, alter the encodings, then how does it work? Like, what was the working behind that feature extraction method? Can someone explain to me?
What was working behind the feature extraction method?
Yeah, exactly.
So the feature extraction was like already a pre-trained transformer on text data. So basically it was probably trained on potentially some other task. Maybe trained on classifier. Well, it was trained as a language model probably, which is like predicting the next token in the text.
Yeah, okay. Yeah.
And doing that will lead to a fine kind of feature extraction generally. So basically, you'll get from the encoder, you get like features that you can then use for classification.
Yeah, since it's a BERT, it's probably mainly masked language training.
Yeah, okay.
Mm-hmm.
Yeah.
So
And
we
then
do the
next
same
sentence,
with
depending on the version.
So we do the same here with our training data set. Is that what?
Well, that's
Like,
called what we just described is called pre-training, but now we're doing what task. We're fine-tuning via a classification task.
Mm-hmm.
Different.
Okay, so I was confused where how do we get this hidden state out if we don't change the gradient, so nothing like then
Are you talking about the fine tuning or the previous?
the feature extraction, the transformers as feature extractors section.
So how do you get the hidden state?
Yeah.
So the encoding layer is what produces the hidden state. So we preload an already trained model or pre-trained model, and then we load we just feed an example to the model and take like the hidden state of that model. Does that make sense?
Yeah, okay. I was wondering what was happening that in between, like we pass in our sentence, I mean with our tokens, and then we get the hidden state. Like, what was happening in between? That was my question. Like,
yeah. So
is that
so we do load the model from Hugging Face. So like auto model is from pre-trained, and then it uses the model checkpoint, which is still based on case. And then
let me try. After this, here's the thing that's different between this one and the next one we'll be doing here. The thing we still forward propagate, so we kind of give the new inputs which have to do with our new data, and get the outputs, that is the encoding or the hidden states as a result of the encoder, but we do not allow the network from the start of where we give our inputs up to the output of the hidden states to learn anything new from the set of inputs that we are now providing it. We just allow it to go from the input and generate whatever hidden states it would have generated based on the weights and the data that it acquired from the pre-training. So because we have frozen it, we don't allow the backward pass that would typically happen to fine-tune those weights to the new data. So the data just flows, think of it abstractly as the data just flowing forward with no adjustments to the network weights within the transformer, because the transformer weights are frozen in this case. So it just takes the input still that we newly provided, that is the tweet tokenized data, takes it forward and generates a set of hidden states. That's it. But the hidden states that it generates is totally based on the pre-trained weights.
Yeah, that makes sense. Yeah.
Mm-hmm.
Thank you.
So yeah, so we mainly use this in feature extraction. Think of this like a black box. We get it from Hugging Face.
Yeah.
Tokenize the words, and then we feed the data through this black box and then get whatever is output and put it through a classifier. So you see it here where it's explicitly, it's feeding the input into the model. The model is what we got from Hugging Face. And then it's getting the outputs, and the outputs has the last hidden state.
Okay, so we don't alter the model, we just alter our inputs and it's like, okay. Like
we feed in inputs and then just get what's output, but we don't alter that model.
Okay.
So this model is fixed, but the classifier that comes afterwards. So
okay, so we use in this case we use a linear regression layer, I think, like linear regression using sklearn, I think. Yeah, that makes sense.
Logistic regression, and then this is whatever came out of the model, and we feed it in through with sklearn. So this is happening since it's logistic regression and it's simple enough. You could do this on the CPU. So I think this is just doing it on CPU.
Thanks. That's it.
So the next thing is fine-tuning the model. So we have the classification head, but we're propagating gradients through the whole network, including the encoder. So in this case, it does auto model for sequence classification, which is the Distilbert model plus a classification head that Hugging Face provides, I believe. I'm not sure if this classification head is the same as logistic regression. But yeah, this comes with.
I think it would be if you just have one class. I think that makes it logistic regression. Number of labels equals 1 instead of 6.
Logistic regression is usually binary, so just deciding between two classes.
Okay, yeah, of course. It's just drawing a line between the two.
Yes, I believe in this case, logistic regression with multiple classes is just softmax regression, but it's using the same name for both. I'm not sure.
They're not being equivalent because, they weren't trying to compare, see how well neural networks work. Otherwise, they use something like an SVM or this more state-of-the-art from scikit-learn, non-neural network. But anyway.
Yeah, so this is a softmax regression, but it's practically, softmax is just logistic regression, but with more classes. multi-classes.
When I read the paper, the chapter, I understood. I believe that it's that both the one layer which we have now over here and the logistic regression are more or less the same structure. So the difference which we see in performance comes from not from the head of the classifier at the end, the yellow one, but the fine-tuning the model itself. So that if you would, so I understand that the logistic regression which we had in the first scheme and the second scheme, they basically have more or less equivalent structure. They use a fully connected linear layer and the softmax. And the difference between these two approaches is whether you do the training on the main part of the model as well or not. And as the result, because so fine-tuning the whole model gives you much higher precision in the end, much higher accuracy.
Yeah, that's what I got as well. Although I don't exactly know underneath the hood if it's the same, but I think they're comparable at the very least. Yep. Yes. So yeah, I think it's using like a softmax. Well, it's definitely using a softmax, but I'm not sure if it's one layer. But I think the classification heads are comparable. And then it evaluates the accuracy of this fine-tuning. So it trains the model on 2 epochs. And it gets a much better training accuracy, which is I think this is training accuracy, or this might be validation accuracy. But the whole point is the accuracy went up from around 60% to 92.3%. And the F1 score is also a lot better than what we've previously seen with the feature extraction. And that's a general pattern, is like fine-tuning the whole model is almost always, in a lot of cases, going to perform better than a fixed feature extractor, just for the nature that you're tailoring more things to work well with your data. It comes at the cost of computation, of course. So you could do the feature extraction, train the classifier. That could happen all on the CPU, whereas because you're backpropagating and fine-tuning through the whole transformer, that would require a GPU in a lot of cases.
I have a question going back to the imbalance. We didn't balance anything, right?
No.
We didn't do anything like that, but we still got a pretty good F1 score. I mean, so it makes me question the idea that imbalance sets are as important in DNNs or in transformers specifically.
I think like a 5-to-1 imbalance with like 6 classes is like not the worst case, but they're like cases where, I mean, sure. I guess for binary classification, the main kind of example for like data set imbalance is like classifying rare diseases.
Sure, or hate speech too, that has that same problem. Teeny amount of your data is going to...
Yeah, it could be like 1% of your data as opposed to...
So if you balance your set and we do this again, maybe we gain a fraction of a percent, but maybe it also makes it more robust anyway, to real life inference. So you may want to do it anyway, even though it doesn't help your score. It's still a good idea, I'm guessing.
I would say for like this example, it doesn't really matter too much to balance your data set, like maybe
Yeah.
you would gain like a few accuracy points, and it'll be more robust. But I guess you could always think of cases where the imbalance would matter. And I think it's just calling out that when I was talking about the imbalance, it was calling out that you may have to deal with it. But in this case, you don't have to deal with it that much. Yeah, so it does get a pretty good F1 score. Actually, this is the testing accuracy from based off of this part of the model. So yeah, this is the testing accuracy. Testing loss, this is just the log loss for softmax. And then it gives the runtime, samples per steps and steps per second. And then it uses the kind of greedy rule to decide what the final class is, which is just taking the argmax or the max label of your output predictions. So your predictions are the output of a softmax layer. So so the shape of your predictions would be 6 classes per each sentence, and these 6 classes will have like a number between 0 and 1. That is the probability of the model, the probability according to the model that sentence is that emotion of that class.
And this is where that neutral comment could matter. I'm surprised it doesn't matter more, but a little bit, because you don't have a neutral class in here. So
Yeah.
it has to take the max. You're not even putting a threshold at all. You're just saying take the one that's most likely, even though it might not be any of these.
Yeah.
That's the point where you guess. So that's exactly the point where you say guess if you don't know. And where if you would have a neutral class and you would say, well, don't guess, tell me that you're not sure. But
yeah.
That's exactly this line, the ypred is equal to argmax. That's the line which asks for guessing.
Yeah. So the predictions are basically like how late it's the model saying like this is likely to be these classes. It gives like a probability per class. So all of them add to 1, and then argmax is take the most probable.
Yeah, and this is also not multi-label. Like when I talked about my specific situation I'm dealing with the taxonomy, multi-label is very important.
Yes.
So almost all these examples are like small classes, and they're not multi-label.
Yeah.
So, but anyway,
Yeah, so they plot the confusion matrix. It's much better than the previous confusion matrix, where like most of the mass in like the surprise examples was in joy and fear. You can still see that there's still like some amount of mass, like 20% of the mass in joy and fear. So surprise still gets confused very often with joy and fear, but it's a lot better now than it previously was. I think previously it was like above 50% wrong. But in this case, surprise, it's only 20%.
Can I go back to the question about multi-class, multi-labels, just to make a point over here? I think with Hugging Face, you have many different tasks, including multi-label labeling, and you more or less go through the same structure over here. You take any good pre-trained model which understands your base language, independent of the task which is doing, and then you put on a head for classification, and you have multi-label classification heads as well, so that's not a problem. Now, the second issue is that the more difficult your work is, the more difficult it will be for you to get good numbers. Sort of multi-label is just changing a line in the code to say, I want to have multiple labels, and that's easy to ask for. To get good quality output depends on having good data and training well. Sort of it's just more difficult to do. But in terms of structures, Hugging Face does support multi-label equally.
Okay. Yeah, and then fine-tuning with Keras, probably won't go over too much over this, but this is just doing the same thing, but in TensorFlow, as opposed to Torch. And then afterwards, they do some error analysis, so they plot the top 10 wrong examples. So like it's confidently wrong. So like the probability is probably high in some, well, the loss is high. But intuitively, it's like it's confident in another class. But it's labeled, and it's the class that it's confident in is different from the label, I should say. So in some of these cases, usually because of mislabeling, which happens in every data set. But yeah, we can see examples, and you can kind of see patterns on why it's like overconfidently wrong. And then a lot of cases, like the classifier may be right, but the data set is actually wrong. So,
I have a general idea of what the loss is. Can someone explain that again for me? In the neural network, where the loss is coming from? Number.
So the loss is coming from the softmax loss. I think it's called log loss as well. There's other names for it. Let's see. Yes, I believe this is the loss that's using, this is for binary though. But basically, the output of the softmax layer is the probabilities So the log loss is like your negative log likelihood. So you take the log of all the probabilities, and you're basically picking out the log of the probability that is of your label.
So are you intuitively just saying of the 6 probabilities, they're all so close together? Like this one is not very different than the other 5 in this case. So like the system couldn't really have that much certainty because like 0.5 probability and all the others were 0.49. So it's a case where that's the intuition, where it's having a hard time distinguishing between the classes, which is most likely.
So it may be very confident in one class, but that class may be different from the label, so that it is. And okay, I guess maybe I can re-explain it. But the log loss basically is taking the probability of your labeled class and then taking the log of that and negating it. So if your probability is, so if your classifier is predicting for that label the probability of being very low, so in this case the label is love, and let's say that your classifier predicted that the probability is very low, then your loss will be really high because you're
I
taking
get it.
log
I
of
get it.
a
You're finding where
small
it's
number.
most. You're finding where it was most wrong. Sort
Yeah.
of.
Yes. Yep.
Yes. Mhm.
Yeah,
Or it
and
thought
there are two components to
it
it,
was
right?
all
One is
cocky.
the,
Go
sorry,
ahead.
go ahead.
Sorry. No, go.
So
please.
I was saying that there are two components, right? One is the level of confidence, and the other is it the right class, and if it predicts the wrong class with high confidence, then so that you want to penalize the model when it is wrong and when it is highly confident that it's wrong.
Yeah. Yeah.
So
Right. That makes sense. So you're finding the
That's-
most egregious examples.
exactly.
Yeah. In a lot of cases, it may be wrong labeling. So, or quirks of the data set, as mentioned here, where like maybe.
So, if we were training, if we were using this as a training rather than just inference, that log loss, that would be used in the classification head to adjust the weights in the head, to reduce that.
Yes.
Sort of,
the log loss is reducing the weights in the head. Well, the log loss is what is used to train the network in this case.
Yeah, yeah. So you're basically saying there are so many different examples it has to make decisions, and so some things can't be adjusted for. And I get it.
Yeah.
I get it. Okay, thank you.
Yeah, so it's just getting some intuition on the data set, and you can choose to like how you. Basically, it's up to the person training how they deal with this information. Like they could say, oh, it's just the quirk of the data set and my classifier is performing well anyways, so I'm not going to change it. Or they could look at it and say like, oh, maybe I do need to retrain or train a model more. Or there could be like a pattern that it's missing. And you also want to do it with the correctly classified examples as well. So it's looking at confidently correct examples. So examples where got the answer correct and it's very confident about it, so the loss is low. In this case, the you mainly want to make sure that it's not finding shortcuts in your data. So like there's no pattern that is too simple for classification that it's picking out. Or you want to make sure that in some cases it's not overfitting to like to service level information, like the length of your text, or maybe if there's a word in your text that always appears in the confident examples, it's just remembering that one word, no matter what the context is. In fact, a lot of these examples have ungrateful. But yeah, you can also choose what you want to do with this information as well. I mean, there's not really like a standard way of a standard like flow chart of dealing with this information. But yeah, you want to look at the confidently wrong examples and the confidently correct examples, just to make sure that your model is doing what it should be doing and not memorizing sentences, let's say. Yep. And then the last part is just training and saving the models. You can save it to Hugging Face Hub and then use the model checkpoint to kind of get back the model as well. Yep. And I think that's...
Thank you very much.
Yeah.
Yeah, thank you very much for nice and good presentation. So one quick thing I want to ask the group, the authors of the book want to come and have a chat for Q&A. They are suggesting when is good. So I'm thinking like, do we say after we finish the book club? What do you think?
I think that we should do it maybe when we're 2/3 of the way through, right? Or
Yeah,
something,
okay.
because then we'll have a lot of info, a lot of context, but there'll still be some more learning left afterwards, if possible. That would be, there you go.
Okay, thank you very much. So I will inform them that, maybe we can just get one of the weeks at the middle of the book and let them know that that's good for us. Is that okay with everyone? Okay.
Yep, I think around 2/3 would be, as Darren said, because we want to get through the majority, but maybe not wait till the end, but somewhere past the midpoint. So 2/3 sounds good.
Okay, thank you, Serena, for the contribution. Yeah, thank you very much, Relenga. This is nice walkthrough, and I really enjoy it. Yeah, thank you all for attending. Next week we're gonna have Transformer Anatomy by Yakov, and yeah, I'm happy to see all of us next week and same time to discuss the next chapter.
Okay. Thank you.
Thank you.
See you next week.
See you next week. Bye-bye.
Bye-bye.
Bye.